And now, the mole. Cute, aren't they? But we're actually not talking about the star-nosed variety of this mole, which is what this is. The mole is the actual SI unit of amount. Now, amount in everyday English and weight or mass are all thought to be synonymous. But in scientific definitions, amount and mass are two very different quantities. Now, they're related, but they are different. And amount is actually just the number of things that you have. Now, what we're going to talk about here is the mole is named after, or was originally figured out by Count Lorenzo Romano Amadeo Carlo Avogadro. Remember that name, or at least the last one. All right, amount. So you already know some units of the quantity amount. And for example, number one is an individual unit. One thing. A dozen is another unit of amount and is equal to 12 individual things. You might even know what a gross is. A gross is 12 dozen or 144 individual amounts. What is another unit of amount that you're familiar with? A pair. A pair is 2. So now you're just going to learn a new one, and that is a mole, and that is 6.02214 times 10 to the 23rd individual units. And this particular number here, that 6.02 times 10 to the 23rd, is referred to as Avogadro's number. So hence the statue of the guy. All right, why is this important? Well, let me give you an example. All right, in a parallel universe, in arts and sciences, room 128, which is where the lab is back when we had classes face-to-face, a student goes to the lab and opens up their lab manual or their handout and is told to dissolve 8.79 times 10 to the 21st molecules of sucrose into 3.34 times 10 to the 24th molecules of water. Now, in real Earth, or real VAAS, AAS 128, you are told to dissolve 5 grams of sucrose into 100 grams, or 100 milliliters of water. Now, these things are exactly the same instructions. And the important thing is, who's going to finish first? Now, envision, again, this is 8.79 and then 19 zeros, 3.34 and then 22 more zeros. Even if you could individually isolate the sucrose molecules and place them into the beaker, it isn't, you could never count that high in a lifetime, or in many lifetimes, or even in millions of human lifetimes. But you can weigh stuff pretty quick. Put it on the balance, hit a button, number reads out. Same things for weighing the water or measuring the volume of water. We have cylinders, they're marked, you can read them. So counting insanely large numbers of small things is tedious, but the important thing is that the amount is actually the chemically relevant quantities. Things react mole to mole or molecule to molecule, not gram to gram. But we need a link between the two, and this is what the rest of the lesson, or what the rest of the unit is covering. And the good news is it's actually really simple, and it's something that I think you already know and well enough that you can actually do it in your head. All right, so anyone thirsty? Now, back when we actually met in a classroom, I would ask someone if they happen to have a 1 liter water bottle on them. Usually someone does. And the important thing to know is that a filled 1 liter bottle of water weighs about 2 pounds. So let's say that keeping hydrated is very important to you and you have determined that you need 9 of them to get through the day. What mass of water or what weight of water are you going to be carrying around when you leave the house in the morning if you have 9 liters of water on you? Now hopefully you just did this in your head and came up with 18 pounds. Question is, how much? So this is, think back to when we did dimensional analysis and think of equality statements and conversion factors. Because this is probably what you did in your head, but so quickly you didn't even actually realize it. So we have an equality statement of 1 bottle is equal to 2 pounds of water. So then let me ask you another question. Let's do it the reverse direction. If you had a pile of water bottles that weighed 68 pounds, how many bottles are in that pile? So again, get used to this construction for solutions. But you've got a starting point, 68 pounds. 1 or more conversion factors, in this case, 1 bottle over 2 pounds. In this case, pounds cancel, and then this tells you that that 68-pound pile of water bottles contains 34 bottles in it. Alright, so let's go from being thirsty to potentially being hungry. So again, when we met face-to-face, I had a bowl of M&Ms in class, and I would go around and ask folks how many M&Ms they thought were in there, and sort of tally their answers, and it would be all over the place. And I would, with complete confidence, say 288. And then I would distribute the M&Ms so everyone could count their own little handful of them. We add everything together, and I would, of course, be completely correct. Actually, if I was off by more than 1, that would be a bad day. And did I sit there and spend a lot of time before class counting all the M&Ms in the bowl? And the answer is no. I spent a small amount of time weighing them. So I happen to know, because I weighed a few of them and got an average, that the average mass of a milk chocolate M&M is 0.064 grams. And then I weighed all the M&Ms in the bowl. And let's say, for example, that day I poured out 248.8 grams of M&Ms. And this statement right here is an equality statement. 1 M&M equals 0.864 grams. So that equality statement is used to build a conversion factor between the mass of the pile of M&Ms and how many individual M&Ms there are, and that's how I got the 288. Now, let's say that you worked at the M&M factory and you dealt with large numbers of M&Ms. Actually, even people in general never deal with individual M&Ms. But you could still talk about dozens of M&Ms at a time. Now, what's the mass of a dozen M&Ms? Well, if you know the mass of 1 M&M, and if you multiply it by, fact, again, get used to this problem-solving scheme. Starting point, the 0.864 grams for 1 M&M. Conversion factor, there are 12 M&Ms and a dozen M&Ms. That means that the dozen M&Ms reliably have a mass of 10.37 grams. And you could even give this number or a name. You could call it the dozen mass. And that's defined as the mass of a dozen M&Ms. And it's also a conversion factor, right? All right, so a dozen M&Ms is 10.37 or 10.4 grams. So I could also describe the amount of M&Ms in my 248.8 gram sample in terms of dozens. And I could just say that I've got 248.8 grams of M&Ms. Each dozen of M&M clocks in at 10.37 grams. That gives me 24 dozen M&Ms. Same thing as before, except I'm using just a different unit of amount. Before I was using individual, and now I'm using dozens. Alright, so now let's think about this in the other direction. You know, if I knew I had 45.2 dozens of M&Ms, what would the mass of that pile be? Well, our dozen mass, or in this case its inverse, is actually how we would do this. So I know I've got 45.2 dozen M&Ms. Each dozen clocks in at 10.37 grams, which means that that pile of M&Ms has a mass of 470 grams. Now, in chemistry, this is a very critical thing. We want to be able to easily convert between the chemically relevant amount and the easily determined mass, because unfortunately there isn't an easy way to determine amount directly. All right, and for chemical purposes, a dozen or a gross aren't even enough. So we defined this new unit of amount, which is a whole bunch of things, called a mole. And so while a dozen is 12 things, a gross is 144 things, a mole is 6.022 times 10 to the 23rd things. That's all there is to it, but it is the same concept as a dozen, and that is a concept that I think you know quite well. And again, this is a unit of the quantity amount. And why are we doing this? Well, again, when you're dealing with large numbers, it's usually easier to weigh a pile than to count all the individual members in the pile. But this only works if the items all have a consistent weight, which is, in the case of atoms, that is a very reasonable assumption.